For my first example on proof by mathematical induction, I'm going to prove the result that the summation from r equals 1 all the way up to n of 1 over r times r plus 1 is equal to n over n plus 1. Proof by induction involves two major steps. The first step is called the basis step, where we prove the first case to be true. Now here we have infinitely many cases. The first case is when r takes a value of 1. R goes from 1 all the way up to n, and as I mentioned before, n is an unlimited value. N could be 100, it could be 1,000. So we cannot individually prove every single case because n has no limit. However, what we seek to do in the second step, which is called the induction step, is to show that if the general case is true, then the very next case after that is also true. And once we are able to show this, then we will be able to complete the proof. So I will show you in just 1 second. The first thing to do is to give this result, which is called our proposition. So we are trying to prove this proposition. We give the proposition a name. So we're going to call it P of R, and R takes values given by n. So n can range from 1 up to some unlimited number. So let us take the basis step first. So always in this order. The basis step seeks to prove the very first case to be true, and that is when r takes the value 1. So r equals 1 is our first case. So on the left hand side we have 1 over 1 into 1 plus 1, and that's equal to, in this case, our n. Our r is equal to n, which is equal to 1. So on the right hand side n over n plus 1 becomes 1 over 1 plus 1. And as we will see, both left hand side and right hand side is equal to a half. That checks off. So our basis step has been proven. Now we can move on to the induction step, which is rather more long-winded, but this is actually the all-important step. So the induction step begins with an assumption. We assume, always we begin the induction step by assuming the proposition to be true. So we assume that P of R is true. Now, if our proposition when r is equal to n is true, we must show, this is the crux of the inductive step, we must show that the very next case, which is r equal to n plus 1, is also true. So that is, i.e., that is, we assume that r going from 1 to n of 1 over r into r plus 1, we assume that that is equal to n over n plus 1. We assume this to be true. So our task reduces to showing we must show that the statement P of r equals n plus 1 is true. So I'm going to write that down. So r is going from 1 to n plus 1. 1 over r into r plus 1. And that's equal to, remember, n plus 1. So wherever we see n, we now substitute it with n plus 1. So n over n plus 1 becomes n plus 1 over n plus 1 plus 1. Good? So we have replaced n with n plus 1, which means that this is n plus 1 over n plus 2. So we must show that this here, this is equal to n plus 1 over n plus 2 to prove our inductive step. Now, summation from r equals 1 to n plus 1 of 1 over r into r plus 1 is equal to, so I'm summing all the terms from r equals 1 up to n plus 1. That is the same as if I sum all the terms from r equal 1 to n and then I add on the n plus 1 term, which is going to be, remember the general term is of the form 1 over r times r plus 1. So the n plus 1 term is where I'm substituting n plus 1 in place of r. So 1 over r into r plus 1 becomes, anywhere I see an r, I'm going to put n plus 1. And then r plus 1 will be n plus 1 plus 1. By our assumption, this is equal to n over n plus 1. Remember, that's the assumption we made up here. So this reduces to n over n plus 1 plus 1 over n plus 1, and this is going to be n plus 2. Great. So continuing from here, so there we go, n over n plus 1 plus 1 over n plus 1 by n plus 2. We have to simplify this. Now the common denominator of n plus 1 and n plus 1 by n plus 2 will be n plus 1 by n plus 2. Remember, what we're trying to show is this, n plus 1 over n plus 2. Good. Now n plus 1 goes into n plus 1 by n plus 2, n plus 2 times, and then we multiply by n. So this would be n by n plus 2 plus 1 over n plus 1 by n plus 2 is already over the common denominator, so that's just going to be 1. Now we will simplify the top. This will be n squared plus 2n plus 1 over n plus 1 by n plus 2. N squared plus 2n plus 1 over n plus 1 by n plus 2. Now the top is a quadratic that's going to factor to n plus 1 by n plus 1. N plus 1 by n plus 1 gives us n squared plus 2n plus 1 over n plus 1 by n plus 2. N plus 1 will cancel on top and below, and we get n plus 1 over n plus 2, which was what we were trying to show, and therefore the inductive step checks off and our proof is complete, because we have now proven that if the nth case is true, then the n plus 1th case is also true. This is actually what I like to call the domino effect, and we use the domino effect anytime we're carrying out proof by mathematical induction. So as long as I can show that if the nth case is true, then the n plus 1 case is also true, and I have already proven my basis step, then I am done. For example, the basis step is when n is equal to 1. Now, if I have shown that for the general case, the nth case is true, then the n plus 1th case is also true. That means if the first case is true, then the second case must be true. And if the second case is true, then the third case must be true. If the third case is true, then the fourth case must also be true, and so on and so forth, going all the way up to n, where n is an unlimited number. So the first step, again, let me just run through, is to give the proposition a name, then to prove the basis step, which is the very first step, and then we assume that the nth case is true, and we attempt to show that once the nth case is true, then the n plus 1th case is also true, and by the domino effect, we would have proven our proposition to be true.